This is 3.1. We're exploring polynomial functions. Anthony, yeah.
Beth knows that linear functions result in graphs of straight lines, while quadratic functions result in parabolas. She wonders what happens when the degree of a function is larger than 2. Beth searched for polynomials on the internet and found the following table.
Okay, these are polynomial expressions. These are not polynomial expressions. So, we've heard the word polynomial quite often, and usually we think of it as something like x squared plus 3x. This is a polynomial. This is also a polynomial. And this is also a polynomial. Or sorry, this is a monomial, one term, right? We have a word for this, we call it the trinomial. And then polynomial is basically more, it actually does include one, okay? Believe it or not, even though polynomial is really referring to a plural. It does include one term. So you can see it right here. This is a polynomial. It has one term down here, minus 4x. Minus 7 is still also considered a polynomial. Okay? So we kind of think of it as more than one or two. We have the words monomial, binomial, and trinomial, which should be familiar to you guys. 3 terms is a trinomial, 1 term is a monomial, and 2 terms is a binomial. Trinomial, but all 3 of these are considered polynomials. Okay, so the question is in today's lesson, and this is kind of the whole story right here, is what is a polynomial and what is not a polynomial? So what makes a polynomial and what doesn't? So we're looking at these expressions here and trying to see what's in common between these expressions that's not in common in these expressions. So what makes an expression a polynomial? And what do functions that involve polynomial expressions look like graphically and algebraically? That's what we're going to figure out today. So A, look carefully at the expression in the 2 columns of the table. What do all the polynomial expressions have in common? So we're just looking at this first column here. Luke, what do you think? What's the common thing here?
I would say x, but negative 7 doesn't have one.
They all involve an x variable, okay.
But negative 7 doesn't have one.
Yeah, so that's not actually true then.
Involve a negative or a subtraction sign.
They all involve a negative or subtraction sign?
In some way.
Okay, yeah. It's kind of... You're right. That's not really... That's a little bit out there.
I don't know, I feel we can't figure
Yeah,
out.
it's hard, right? It's hard. It's not evident at first. Anybody else? Marco at the back. You got an idea?
They're all integers. I don't know.
So is the other.
Okay, they're all integers. So they're all whole numbers here, right?
Yeah, well, it could be factored.
What about this number here, 2/5?
Pardon?
2/5, you're okay with that? It's a fraction, but it's not a whole number. You're not sure, right? Anybody else? Okay, so the key thing we want to notice actually is the power of each x variable. So the power is an integer. It's a positive integer whole number. Okay, so there's no fractions in the exponents. Okay, so this x is 1. This x you can consider, would just be a 0. There's no negative or fractional exponent to the x variable here. Okay, whereas if we go here, we can see -2, -1 here. We see this is a root x, which you guys should know is the exponent of what? Root x is the exponent of a half, right? So root x is equal to x, the exponent of 1/2. Everyone knows that, right? Okay, so what we find here is happening here when we know 1 divided by, when we have x on the denominator, we see that this is actually 1 times 2x plus 5 to the exponent of -1. You guys know about that as well, right? That when you have a negative exponent, you flip. So the real difference here is that all of the x variables have positive whole number exponents. Okay, I'm going to say that one more time. All polynomial expressions, the x variable has a positive whole number exponent. Not just one of the terms, all the terms in the polynomial. Okay? So that's what differs a polynomial from a non-polynomial expression. Okay? So the expressions in the right column are not polynomials. How are they different from the polynomial expressions in the left column? They have fraction or negative. I'm not on. Oh, yeah. Or negative x exponents. And this one, how are they? What do they all have in common? They all have positive integer exponents. Another way of saying this, and kind of the terminology that the book will use, they'll say that the polynomial, I'm going to write it here, okay, it's kind of a different way of saying all have positive integer exponents, right? But you'll see this a lot in the book, and it's in the definition, so I wanted to write it out and answer any questions you might have about it. The polynomial expressions all involve only the sum of constant multiples of non-negative integer powers of x. Non-negative integer powers of x, positive integer exponents. Okay, it's the same thing. And it's the sum because you're adding these up or subtracting them. When you add and subtract, we still use the reference of a sum. And constant multiples, so these values are constants and they're multiplying. Any questions about that? So in your own words now, define a polynomial expression. Gianluca, can you try? It's not on here, you don't have to look. Just based on what you heard today, how would you describe a polynomial expression? No, it doesn't, because there's no exponent here. You could argue that there's no exponent here, really. Yeah, okay. You want to try again? Someone else? Everything we just talked about. How would you say a polynomial expression? How would you define it? Define a polynomial expression. This is important, right? You want to be able to know what it is. Alex.
It's an expression with all positive whole number exponents.
Yes. I'd ask somebody else, but that's pretty perfect. Okay? That's as simple as it gets. It's an expression, all whole number positive exponents. The only one that's a little tricky again, and this is the one that Luke mentioned, is the -7, because you don't really see anything here. It's just a constant, right? We know when we have y equals -7, though, we know what that is, right? We just go to -7 and, sorry, -7, and it's just a line down here. So it's just a straight line. Okay? Here's -7. This is nothing. Any questions so far? All right. Now this is the reason I'm not having you guys do this, investigate yourselves. It's actually really long. There's a lot of kind of busy work, but we're gonna sum it up, and you guys will have a chance to copy it down later by looking at the video. Next one, it says the simplest polynomial functions are functions that contain a single term. Use a graphing calculator to graph each of the following polynomial functions, then copy and complete the table. So here's where your phone app comes in handy. You should, if you haven't already, get one you like, okay? I know I've been kind of hinting at that. I've said it several times now in this course. You really need to go and do that. Most of you guys have smartphones. If you have a laptop, there's a great one. I think it's called TK Graph. It's a Chrome plugin or a Chrome extension if you use the Chrome browser. But I mean, there's no excuse by now not to be able to graph something. Like, this is not going away. It's going to help you guys in calculus. Your ability to just punch something in an app that you like and get the graph is going to be, you know, very valuable. So if you haven't done so already, please do so you can see those graphs. I'm going to show you in a minute what they look like, okay? So you don't have to do that right now. Use a graphing calculator to graph, then copy and complete the table. So here's what it looks like. Okay, the first one, y equals x, or f at x equals x. We should all be familiar with what that graph looks like, right? It's just a straight line passing through the origin, okay? Once we have the graph, we should be able to finish the last three columns, all right? The first is the description of the graph, the domain and range, and then the existence of any asymptotes, okay? So, the type is linear. This is all given. This first column is given. The description of the graph. It's a graph of a line passes through 0, 0, 45-degree angle to the x-axis. The domain xer because it goes on forever, and the range yer because it goes up forever. Okay, there's no asymptotes. Y equals x squared, another one that we're completely familiar with. If you were in my class, you learned this step pattern. 1, 1, 1, and you can identify these points very quickly. 1, 3, 1, 3, 5, right? 1 over 1 up. 1 over 3 up, 1 over 5 up. Okay, and that's our y equals x squared. Now, we haven't really looked too much at this. I don't know if you've seen much of y equals x cubed in grade 11. Have you guys? Okay, so this is kind of where grade 12 starts, right? This is grade 12 down from here. It gets actually pretty funky. We get into, you know, exponents of 7 in this course, as high as 7, okay? We don't spend a lot of time there, but we should know what they're doing, what's actually happening on that graph. Okay, that's what you would, you know, define as an advanced function, would be kind of this range here. All right, so we know this is cubic. Why? Because there's a 3, and we know the graph looks like this. Why? Because we punched it in our calculator, right? So that's all. That's how we know it looks like that for now. Okay, and then we can describe the graph. We say, as the graph increases from negative infinity to infinity, it flattens out around the origin, so we get this kind of pattern happening. All right, and then we know our domain is xer and our range is yer. And we know that because this goes on forever in the x direction and also up and down in the y direction. And then there's no vertical asymptote. So this one's pretty simple. Next, x to the exponent of 4. So you should notice something here, that this graph and this graph, x to the exponent of 2 and x to the exponent of 4, are very similar, okay? The only difference is that this graph actually, it looks a lot flatter near the origin, and then it takes off a lot quicker, okay? So the slope is a lot steeper as you progress, okay? So the graph looks like the graph of x squared, only much flatter near the origin. And then you have your domain is the same, and your range is the same as your y equals x squared. So it's above and equal to 0. And there's no asymptotes. Next, we look at the quintics function, which is x to the exponent of 5, and we notice that it is the same as x to the exponent of 3. Now it's flattening out near the origin. Okay? There's the graph. So the graph looks at like x cubed, and it flattens near the origin. So who could tell me what this graph might look like if I said f at x to the exponent of 10? If I were to draw that graph, you should already have an idea now. Yeah, Gianluca.
Should be even more flat.
Right, so it's gonna look something like this. Right? It's gonna be a variation of kind of this, but even more flat and then almost straight up. Okay? But you should also know the domain and the range for this function as well. Yeah.
Is it really more flat though? Because it's the only reason for that is getting more flat though, isn't it? Because of the scale. That
Yes.
we're using?
Yes.
So it's not really more.
It is, you should go on the graph.
Well, the way it looks is more flat. Yes, you're right though, because you can see the scale here, right? This is at 100 and this is only at 8. So exactly what you said is right, because it is still going up more. But if you're describing the way the graph looks, you would describe it as flatter at the origin. Okay? It's kind of really, you're right. It's just we're limited in kind of our vocabulary of how to describe it. If you graphed, you know, only this area, right? You wouldn't see that pattern, right? And so you'd be limited to how you could describe the way it looks, right? I'm going to talk about that for one more second. Just Luigi's point is he's saying that it's not actually flat. If you were to look at this graph at this scale, you know, you would see something totally different. But you're not looking at kind of the overall image of what happens. And the important part in this course is to understand what's happening over here and what's happening over here and over here and over here. And you're going to find out later, okay? Because that allows us to create the graphs if we know what's happening at the ends, okay? Like I mentioned this before, if we only graph a section like this on the graph, what is it going to look like? It's just going to look like a straight line, right? Pretty much. Okay? So the important thing is you need to graph kind of the scale of what's happening and understand what's happening at the endpoints. Any other questions? Good observation though. Okay, so you guys can copy that off the video. D, let's see if we can answer some of these questions now. Which polynomial function in part D have similar graphical characteristics? How are the equations of these functions related? So we talked about this. We said that x squared was similar to x to the exponent of 4, and x cubed was similar to x exponent of 5. So how are they similar algebraically? Kobe, how is this similar to this? Can you see it? Sorry. Can you see this? X squared, how is that similar to x to the exponent of 4?
The exponents are even.
Right. Very good. So how are the equations of these functions related? So even or odd exponents. That's how they're similar. Next, for each function in part D, create a table of values for -3 to 3. Calculate the finite differences until they are constant. What do you notice? So you can imagine for each one of these we did 6 points or 7 points. It's going to take a long time, right? So you guys can copy that and take my word for it. All they're doing now here is they're taking -3, -2, -1, and plugging it into the function over here, x. So when x is -3, y is -3. When x is -2, y is -2. They're plugging it in there, and then they're doing it for the x squared variable. Okay, and what they find is everybody knows how to calculate the first differences. That's what this is, change 1. And the second difference is, right? You're minusing these two values, right? -2 minus -3 is 1. -1 minus -2 is 1, okay? Same thing over here. 4 minus 9 is -5. 1 minus 4 is negative 3. 0 minus 1 is negative 1. And then they're doing it again. Negative 3 minus negative 5 is 2. Any questions on what these tables are showing? Very straightforward, very simple, yes? Okay, so the interesting part is what we find is that the exponent dictates what difference is the same. So like we know, what we've dealt with quadratics and linears, we know for linear equations, the first difference is the same. And we learned in grade 11 and grade 10 for quadratic equations, the second differences are the same. Now what we're finding when we talk about cubic equations, it's not the first or second, but it's the third difference that's the same. Okay? Here we have an exponent of 4. It's the fourth difference that ends up being the same. And finally, for a quintic expression, it's the fifth difference that's the same. I can only tell you guys, if you're doing this on a test, you got to be very careful with these negative signs. Negative is a positive. Okay, that's where a lot of guys are going to mess up. It's where you mess up in grade 11 when you're trying to get second differences. When you're trying to get the fifth difference, it's a lot more likely to happen somewhere along the train. Okay? So when you don't know this is a fifth exponent, and you're making a table of values and you want to check, you got to make sure, you got to be very careful with these. It might be worth writing out, negative 32 minus 243 is equal to, and then write it out that way. Right? Because one mistake here is going to mess up all the way down there. Any questions about that? Okay, a lot of work if you were to do it yourselves, but at the end of the day, what you need to remember is the exponent dictates which difference will be the same. Exponent of 2, second differences. Exponent of 5, fifth differences. All right. What do you notice? So we notice that the exponent dictates the exponent dictates the number of difference that is the same. So x equals 2, x squared, it's the second difference. X, the exponent of 5, it's the fifth differences. Create equations for 4 different polynomial functions that are neither linear nor quadratic. Make sure that each function has a different degree and contains at least 3 terms. Graph each function on a graphing calculator, make a detailed sketch, and create a table of finite differences. So we're going to do this not fully, but we'll do part of it. So I'm going to put this over here. 1, our first equation. So who can pull this off? You're going to create a polynomial function that has 3 terms. And it can't be a degree of 2. Yeah, Luigi.
2x squared plus, 2x cubed plus x squared minus 5.
Very good. That's 1. 2. Alan.
I can do x power 4 plus x, or 2x cubed minus 12.
Very good. Angeluca.
X to the 6 plus 3x minus 5x.
Good. And yeah?
Plus 2.
Plus 2. Okay, good. Yeah, it doesn't have to be 3. Alright, Marco, go.
X to the 7.
You guys are all going to open up? You're all open openers?
Okay, fine. Negative
Yeah.
x to the 6.
6? No, it can't be the same.
Okay, fine. 7.
There's already a 7.
Got something against
There's already a 7.
There's no 7. Yeah?
Plus 5x
Oh, everyone likes the cube.
Plus 5x squared minus 5x plus
Plus what?
plus 3x.
What? You have a 5x here.
Oh, okay, so plus 3 minus 21.
21. Okay. You guys are laughing at his function here. If you turn to your textbooks in a very late chapter, you'll see some very, I don't want to call them dirty, but functions like equivalent to this. And they're going to get worse, and you're going to have to deal with them. And you're going to actually have to factor this, believe it or not. No, there's other tools that you use, not M&A. But yeah, kind of at this point, though, it is laughable when you see something like this. But yeah, you will start to see functions, you know, x to the exponent of 7, 6, 5, 4, 3, all the way down. And then you're going to have to deal with that. So, graph each function on a graphing calculator, make a detailed sketch, and create a table of finite differences. That would take a long time. A very long time. So if you have a graphing calculator, you'd want to do that. We're going to look at a very simple one. Actually, we're not. So they don't do that at all. They just say, the whole point of this is when you find all the finite differences, you're going to find out that which finite difference is the same for this one, Luigi's function. Which finite difference, Kevin? So you're going to make a table of values, right, Kevin? You're going to do x negative 3 to positive 3, and then you're going to calculate all the y values. And then you're going to calculate finite differences between the first y values, second y values. Which finite differences will be the same?
Would be the third difference?
Yes, the third difference, and that's because of the cube, okay? This is just kind of like you guys going through a long exercise to prove what we kind of already figured out here with this table, right? So Emmer, this second one, which differences would be the same?
Second.
No.
The fourth.
The fourth, yes, good. And this one here, Jason?
Six.
And this one here, Joseph?
7.
Yeah, the seventh difference, right? So you have to do that 7 times, calculate the differences, all the way down. So here we show it going to the 5th. For Marco's function, you'd have to do it 2 more times and find out these 2 differences. So in order to do that, if you think about it, we can only get to one number here. If we go 120 minus 120, we can only get to 0. So if I wanted to do the 7th differences of this function, I would have had to take more points. You guys understand that? You can't just take 3 points and be like, well, all the second differences aren't the same, so I don't know what the function is. No, you got to put in more points to find them, okay? So that's important. All right, H, create equations for 4 non-polynomial functions. Make detailed sketches of those equations and create a table. So we'll just do 3. So 1, Emmer, give me 1. That's a non-polynomial function.
Square root of x cubed.
What, like that?
Just that.
So he's telling us this. That's fine, right? You guys understand that, right?
Yeah.
Okay. Okay, Kevin here, second one, non-polynomial. You're coming up with it in your head. There's nothing to read, just a non-polynomial function. So do you remember what a polynomial function is, or expression? It's at the very beginning. Here, we're going to give you Alex's definition to help you out, okay? It's right here. An expression with all positive whole number exponents. See that, Alex? I quoted you, man. You're famous now. All right, so you got one that doesn't have positive exponents. Go ahead. Yeah? How about x to the minus 1? There's 1, okay? Yeah, that's really easy, right?
Over x.
Right, 1 over x, which is a parent function, right? Parent non-polynomial function, right? Good. Daniel, one more.
Alright, keep with the 1 over x. 1 over, like, 3x plus 4.
Good. Which is just a transformed version of this, right?
Yep.
Okay. So then we make detailed sketches and we create a table of finite differences. We chose over here in our solutions, we chose to go with 2 to the exponent of x. Okay, also not a polynomial function. Why? Because the exponent is not a positive, non-negative integer. It's actually the variable itself. Okay, in this exponential function. Right? Okay, we know that graph looks like this. It's also a parent graph, right? So we're familiar with that. But it's definitely it's not. Okay? So a multiple choice question, you're given 4 graphs, you see one that looks like this, it's an exponential function, and you see 3 others, one that looks like this, one that looks like this, and one that looks like this. This one is going to be the non-polynomial function. This one. The one that says right under it. Okay. So, it says, calculate all the finite differences. Look at this. We check 1, not the same. Check 2, not the same. Check 3, not the same. Check 4, not the same. Check 5, not the same. Keep going forever. It's never the same. And you can check all. Wow, they made a mistake here, I think.
Sir, can you just plug in like say like an exponent of half and see if it works out? And if it does, then you know it's not a polynomial function.
We'll say that again. Let me just get to the mistake. They put x to the exponent of 5 here. This should be 2 to the exponent of x, right? Right? Yeah, because like this doesn't make any sense. If x here was -3, this would be -3 to the exponent of 5, not 1/8. Okay, so they just messed that up. So what was your question?
Sir, can you just plug in an exponent of half?
Sorry?
Like a negative exponent of the exponent to the half and see if it exists? Because then you'll get to see if it's a polynomial or not.
So just guide me with your idea. So here's your expression. You want to plug in to x a -1/2?
Yeah, to see if, or even a negative exponent to see if it exists, because then that'll explain if it's a polynomial function or not.
Yeah, but why wouldn't it exist? Sure, it's going to exist if I plug in -1/2 x. It's going to be right here at this point. It'll be like 0.5 or whatever.
But
That won't help us with anything, no.
even if you do it to a regular polynomial function,
No, if you just plug in a value of x, Marco, like let's say you had this, right?
yeah.
Minus x3. You're just going to get the y value at that value of x you plugged in. That doesn't prove or tell you anything, okay? The important thing is to identify that the exponent is positive and it's a whole number, okay? Plugging in different values of x for the x term will just give you the y term at that x point, which doesn't tell you anything. It would just help you graph it, but it wouldn't tell you if it's a polynomial or not. Any other questions? Okay. So we find out that the differences are never the same. Compare and contrast the graphs. Okay, here's kind of the summary right here. Now, we're getting to the end. We're almost done. It says, compare and contrast the graphs, the equations, and the finite differences tables of the polynomials and non-polynomial functions you create. Explain how you can tell whether or not a function is a polynomial by looking at its graph. Okay. How can we tell? Anybody know?
has an horizontal asymptote, it's not a polynomial function.
So no asymptotes. Good. Yep. What else? Yeah.
Can it be if it's neither like even or odd? Because an exponential function is not.
Yeah, because an even or odd always has the asymptote, right? Or no?
No, 'cause
No. An odd function y equals x is a polynomial function. So it could be even or odd. It could be an odd function.
If it, you said if it's neither even or odd, so if it's a neither.
Yeah.
No, because this is neither, right? That's neither, and it's definitely a polynomial function. It's just been moved, right? Remember, even or odd only has to do with the axes,
Oh.
okay? They have to be symmetric about the axes, so that's not true. Yes.
if it's periodic, so like sine or cos.
It is a polynomial or not?
not.
It's not. Good. So its graph, but other than kind of looking at its graph, no asymptotes, and we would also probably put in there continuous. Okay, that's kind of really the two keys.
Can you also tell by looking at, like, to see if it's equivalent to a parent function that you know has, not usually. Like, if you can tell that it's 1 over x, or if you can tell it's root x. just
Yeah.
like,
Yeah, that's true. Yeah, but then 1 over x and root x, they all have asymptotes, right?
That's true.
Yeah. Okay. It's equation. So what do we know about the equation? This is Alex's quote here. Kevin, or behind Kevin, Anthony. What do we know about the equation of a polynomial function? Come on, man. The whole lesson was about this. Sorry? The equation is positive? What's positive?